This is the second part of lecture 9. I just wanted to spend a little bit of time talking about the van der Waals fluid that we had been discussing in class. And just to refresh your memory, we had sort of talked about two particular cases. So I'm plotting pressure as a function of volume. And I said that when the system is hot, so the temperature is hot, T hot here, and by hot I mean RT over V prime minus B is large compared to this term, then the van der Waals equation of state looks like this. Basically, there's no features as you compress the system. But if I were to look at a different isotherm, so holding temperature constant at some other value, then according to the formula, this is what you would observe. And you'll note that I say according to the formula, because as we're going to see here in a minute, what happens in practice is a little bit different. So I had drawn 1, 2, 3, 4 points along this curve here, which I'm going to label 1, 2, 3, and 4. And I want to just give little diagrams of the system that we're talking about, what each one of those would look like. So this might be pressure 1, right? So in volume 1, V, a little bit more clear, P1, V1 might be here. And then if I want to achieve some higher volume, or smaller volume rather, I can put 2 blocks on the top like this. So this would bring me to P2, V2. Or I could simply get to this same pressure and same volume by just building a box that had the same volume there, right? And make sure that it's a very strong and rigid box. I'd still be at P2, V2. So, setting volume constraint gives you a certain pressure, or pressure constraint gives you a certain volume, normally at 1. At 2, this is true. What about 3? Suddenly the fact, I'm sort of making this argument that if you set the pressure, or so if you set the volume at a certain value, you'll get a pressure. Or if you set the pressure at a certain value, you should get a volume. It doesn't matter which experiment you do, right? I'm setting the external pressure through the blocks, I get to a volume. Or if I set the volume, I should get to a pressure. But if you look at the shape of this curve, actually, you can see that for a particular pressure, so let's say this one, 3, there's more than one volume that's possible, right? This, this, and this. So if I were to draw this, that would mean that if I put 3 blocks, so pressure 3, right? 1, 2, 3, this is a volume that would work. 1, 2, 3, this is a volume that would work. 1, 2, 3, P3, right? So this is going to be a volume, a volume, a volume. So we'll call this 3, 1, V3, 2, V3, 3, and P3. This seems odd, and it's actually a signature that there's something wrong with this curve that I've got here. So let's continue to examine this curve. As I've just to really stress this point, the curve that I'm plotting is what van der Waals says is going to happen, the van der Waals equation of state. It's not what you would measure in an experiment. So we're going to examine why there's problems with this curve, and then I'll show you how we're going to actually fix those problems. But before we move on to fix them, let's also see another problem. What happens at point 4 here? So point 4 corresponds to, we'll say, 4 blocks, 2, 3, 4, sitting up top, which is P4 and V4. Suppose that I add a little bit more weight. So I push down a tiny bit more on this, right? It was stable up here at 4, and I put in a little bit more pressure. Well, actually, I can't, because if you look, there is no way to go to high pressure, so that's a little weird. Well, let's think about this another way. Suppose that I just rigidly move this thing back or down a little bit so that the volume compresses a little bit here. What actually happens? It looks like the pressure of the gas goes down, right? And in fact, so that would mean the pressure in the gas is less than the pressure from the block, so then it should go down a little bit further. But then the pressure in the gas is still less than that of the block, so it should go down still. So it actually, the pressure will go all the way to roll here. So this area of negative slope in the PV equation of state is actually unstable mechanically. So there is an unstable region of the equation of state, which is also problematic. The system collapses. So these are the problems with a curve like this, right? You have multiple values of volume which give the same pressure. So it seems like there's 3 different places where this can happen. And moreover, it's clear that the system is unstable with respect to small perturbations. In nature, why don't we see this? Well, the solution to this problem was actually provided by Maxwell. Because what Maxwell realized was that although the van der Waals equation of states had values of temperature where you got this inverted region, he said, wait a minute. As you go up this hill, what if I do the following? Notice that I can do a horizontal line that cuts across here. And there's an arbitrary number of lines that you could do to get through this shape. But there's one line uniquely where the area in this region is equal to the area of this region. And it turns out, by this Maxwell construction, you can plot out the real PV curve that you would find in nature for such a system, where the first part looks the same as before, but where there's a flat region, where as you compress the system, rather than the pressure going up and then down and then back up, the pressure, there's a region where the pressure is actually constant with respect to compression. And the reason for this, the reason that you have that this works of this equal area is going to become more clear in the future once we start to talk about phase transitions. Because in fact, this is what you are looking at. So if I take, rather than a van der Waals fluid, I take something a little bit more familiar, like say steam. If I compress steam, the pressure will go up until at some point the steam starts to change phase. And as it changes phase, it will coexist with water droplets, which will fall out of the steam and I'll continue to close off the volume until all of the steam is turned into water, and at which point the pressure will go back up. So between these 2 points of volume here, everything over here is steam. Everything over here is water. But within this region, there's some percentage water, and there's some percentage steam. And as I move along the line, I go from 100% steam and 0% water to vice versa. So this is called a phase transition. And the prediction of the phase transition, the fact that you get these van der Waals loops, are actually one of the great successes of the theory. because the ideal gas model doesn't allow or doesn't predict phase transitions, whereas the van der Waals model does. And this particular phase transition is called liquefaction. And it's something that we're going to be revisiting later in the course. Okay, that concludes all I wanted to say for now about van der Waals liquids and phase transitions, and I will see you in class shortly.